Meow. Check me out. Hey gang, how's it going? Ready to go here. Got my little helper. See how long he lasts. Alright. We're ready for our next chapter, chapter 8. We're going to start doing chemical and physical reactions. So get your papers out, because here we go. So as we talk about reactions, really, first we need to talk about physical reactions. So a physical reaction is only, a change in appearance. It doesn't change what it is. It's still the same substance. So as we think about examples of that, melting ice is a great example, because it's still H2O. It was solid, and now it's liquid. So it's still the same substance. And that's the key thing with the physical reaction, is it doesn't change what it is. Now, as we think of chemical reactions on the other side, so those are changing what the substance is. It's not the same thing anymore. So there's different ways to have chemical reactions. We'll talk about some of those. But as we think about it, a good example of a chemical reaction is burning paper. So as you burn paper, it's not paper anymore in the end. It's, ash and the dark stuff that's left there. It doesn't have the same tensile strength. You can't write on it anymore. And so it's not the same stuff. So that's the big idea that you're looking at. And we'll look for different evidence and things that we have too. Another reaction that we've seen that was kind of cool was the putting sodium in water. And when we put sodium in water, we saw quite a bit go on there. And hydrogen gas was produced. It ignited the hydrogen gas and blew up, right? So that's another good example of a chemical reaction going on there. Different stuff coming out of it. We checked the water afterwards. It was the pH had changed. It was totally different stuff happening. Another example you can think about is eating food. So as you're digesting food and it goes through your system, it definitely comes out different than it went in. So it doesn't look the same, it doesn't smell the same, it's definitely not the same kind of stuff anymore. It has changed what it is. So evidence of chemical reactions, things to look for. A change in color is a really good indicator of a chemical reaction. So with the burning of the paper, that was a good example. You see color change happen with the paper, and texture change. All those things, look different because it is something different. Another good example is rust. When iron rusts, it turns a different color. It's reddish colored now because it's something new. It's iron trioxide is what the rust is. So that's another good color change we see, and that's pretty good evidence of a chemical reaction. There are a few physical reactions that have color, but not very many. The majority of those are going to be chemical reactions. Giving off gases. So when we burned the paper, smoke was coming off. That was a gas coming off. Another example of this is putting zinc in hydrochloric acid. It's going to release hydrogen gas. We can burn the gas and see that it is hydrogen, and again showing us something new is formed. Those bubbles weren't there before. That's something new. Another piece of evidence is making a precipitate. When we have two liquid solutions come together and make something that is insoluble in water, it does not dissolve in water. So remember, we talked about sodium chloride dissolving in water and getting pulled apart, and we have sodium ions and chloride ions floating around in the solution. That's just a physical change. When you dissolve something, you put salt in water, you get salt water, right? There's still salt, there's still water, it's still the same stuff. But if we mix that with something else and make a solid out of it, then that would be something new. Here you can see there's two clear solutions, and all of a sudden it turns yellow. It's like weird, right? So that is something different. That is a precipitate, specifically happening from two liquid or two solutions where things are dissolved in there, and they meet up, and two of them meet up and lock together that won't get pulled apart. Now, heat is one that confuses people a lot of times because they see heat given off and they're, oh, it's a chemical reaction. But it's not always. I mean, here's a good example, right? Woo! So, there's giving off heat, but I didn't change my skin. It's still skin, it's still the same stuff. So, physical reactions can give off energy too. Remember, that's exothermic, giving off energy. So, don't get bamboozled by heat given off, because you got to think about the reaction. What's causing that heat to come off? And so that's one that's kind of, you got to think about it. And that also goes along with light. If you think of a battery and a bulb, when we have electrons flowing through, and it goes through the tungsten and the filament, and that gives off more resistance as those electrons are forced through the tungsten, but it's still tungsten, and so it gives off energy in the form of light. But again, that's a physical reaction. Sometimes, obviously burning stuff, burning magnesium, we saw that was super bright. But you got to kind of, again, look at the reaction, see where it's coming from. So when we write chemical reactions, one thing that we need to write down is the states of matter. So we put these as subscripts next to things. If it's a solid, these are all lowercase letters when we're doing this. In parentheses as a subscript, solid, S is for solid, L is for liquid. Now, my font isn't very good here, but when we do the L, because it looks like a 1, it would be confusing when you're writing it. We use a cursive L, and I'll show you some examples of this here in a little bit. Gas is little g, so showing that it's in that state of matter. And then aqueous, just like aquatic, aquarium, Aquarius, all deal with water, right? So if something is dissolved in water, it is aqueous. Putting salt in water is not liquid, it's aqueous. To liquefy the salt, we got to heat it up to almost 2,000 degrees, right? It's pretty hot to get that stuff to melt. So that's the difference between aqueous and liquid. As we write down chemical reactions, as we have our things that we start with are called the reactants, and then we put an arrow, and the arrow is showing direction, and we start it, and it points from left to right, and that's the proper direction to show, just like reading left to right. And that shows that a reaction is taking place, and we're changing in this direction. It is possible to have a double arrow, where it's a reversible reaction, where it can go one way or back the other way. So we would show that with the double arrow. Also, on top of the arrow, sometimes we put symbols to indicate things that are necessary for the reaction to take place. The delta, the triangle, is showing that we need a change in energy. We could also see the word heat put in above the arrow, or maybe a specific temperature. We need to reach a certain temperature for that substance or for that reaction to take place. Now, whoops, I needed another slide. Pause. Okay, let's look at some examples and of writing chemical equations. So with water, we talked about this. Oops, let me make that a little thicker. With the water, H2O, and if that was a liquid, like that, we would show it and have the arrow here. And we would need to add some energy to this. This requires electricity to make this happen. But then we can take the water and break it up into hydrogen gas and oxygen gas. And remember, hydrogen and oxygen are diatomic elements, so we would see them pair up like this. Now you may be saying, hey, what's going on here, because there was one oxygen here and now there's two over here. We'll get into balancing the equations later, so just hold up on that part of it, and we'll get into that and work it all out so nothing seems like we're pulling things out of nowhere or things are disappearing. But for right now, I just want to talk about the reactions and the basic part of what's happening with them. So showing this reaction, I'm writing the correct formulas. These are diatomic elements, and so this is the right way that it would be. And this is the right way to write water. There we go. We also saw rust. Rust happens when iron, which would be a solid, is reacting with oxygen gas, again, diatomic, and it would make iron 3 oxide, which we know as rust. And that would be a solid. So we see this reaction taking place here. Again, I'm not balancing it, but we see the setup of what's happening with the chemical reaction, showing that what we started with over here, I should write that out maybe. This side, these are the reactants. And this side is the products. So we have reactants that we start the reaction with and products that we end the reaction with. Now we made a precipitate. I showed you the reaction with the precipitate, and so let's write that one out. Lead to nitrate. So again, writing the correct formulas, always where you need to start. Lead 2 has a positive 2, nitrate's a -1, so it takes 2 nitrates. Now this is going to be aqueous. There are rules that we're going to go through and figure out which things are aqueous and which aren't, but a couple little tips right away. Nitrates are always soluble. Doesn't matter what it's with, it'll get pulled apart in water and dissolve. So lead 2 nitrate is going to be soluble. Now another easy rule to remember is alkali metals are always soluble, with the exception of lithium fluoride. So potassium, you don't need to see what the second half of it is. Potassium anything, potassium carbonate, potassium oxide, potassium, whatever you want, will break apart in water, and it will be soluble in water. So when these two react, we got positive, negative, and they'll switch their parts around. So we can get lead to iodide, which actually does not dissolve in water. We'll see that later in the rules. And that would be our precipitate. This is the part that locks up. Everything was all free floating around, but lead and iodide meet up and it's like true love. You can't break them up. They're stuck together. Now, the other part, we got the potassium, which we said was always soluble, and nitrate, which I said was always soluble too. So for sure, this is aqueous. One more example. If you have ammonia, it's NH3, and ammonia is a gas. If that meets up with water, it's very soluble in water. So we have liquid water here. And what that would make is ammonium, which is polyatomic ion, ammonium hydroxide, which would be aqueous. And this reaction is actually a reversible reaction. We'd have that double arrow there showing that. So here's some examples of how to write these out. Big difference between chemical and physical. Again, chemical is creating something new. All of these here are chemical reactions. We see something different on the other side. If I was to write a reaction for a physical reaction, like H2O, that is a solid. Like we have not very much outside anymore because we have some energy going on, and it has created H2O. That is a liquid, so it's melting, right? So same thing on each side. That's a physical reaction. Chemical is making something new. So there's the first part of Chapter 8. Now you can get working on some homework. All right, see you in class.